Once you're familiar with how to deal with differentiation in a more abstract, purely mathematical sense, you may be asked to apply those concepts to a more practical scenario, taking what you have learned and creating equations based around those concepts from a description or diagram or both. This you may find referred to as modelling. So for these, you may have like some areas or perimeters or volumes that you need to work out, and just work out maybe what the maximum or minimum of those values are going to be. You can, in theory, also work out a rate of change. See, if you've got a container filled with water and it's filling up, you can say, well, what is the rate of change of the depth? This, for specifically called rate of change, is a topic in and of itself in A2, and because of the additional nature of parts of those questions, they're going to have a video all of their own. This here is just more looking at the AS, areas, perimeters, and so forth. We also should say that there aren't too many modelling questions available, at least compared to other topics. So there isn't too much to practice with, but still, nevertheless, we'll want to go over some examples so we can see how we can take a scenario, pick out the relevant piece of information, and apply them. So we're just going to look at a couple of examples here today. For instance, in this first one, we have a diagram which apparently is showing the plan of a pool. Now, the shape consists of a rectangle in the middle, then an equilateral triangle on top, and a semicircle on the bottom. And given that AB equals x meters, that EF is y meters, that the area of the pool in total is 50 meters squared, show that y equals 50 over x minus x over 8 times pi plus 2 root 3 in brackets. Well, if we're going to show this, we need to create some kind of equation in the first place that we can rearrange and solve for y. In order to create an equation, you need an equal sign. Well, what do we have an actual value for? The only number we have right now is the 50 from the area. So let's try to create an algebraic expression for the area and set it equal to 50. We'll split up these areas into the three shapes because that's going to be the most straightforward. Just to label some sides first of all, because this is an equilateral triangle, we're saying that every side is the same length. So if that's x, then this will be x, and then this will be x. Since this is in a rectangle, if this EF is y, then BC will also be y, and then the CE is going to be x. And then this bit around here is obviously just going to be a curve as part of the semicircle. We're not going to have a letter for that just yet. But using these, we can get the areas. So for a rectangle, the area of a rectangle is just going to be the base times the height. So that will just be your x, y. Here, for the area of the triangle, we don't have a height yet, so we can't immediately do a half base times height. If you wanted, you could split this into two right-angled triangles and try to do Pythagoras, but we could alternatively, in one step, just use the sine rule, the area for the triangle sine rule, wherein so long as we have two sides and an angle between them, we can get the area of that triangle. The two sides we know are both x, it doesn't matter which two we pick, and just as how the sides equal in an equilateral triangle, so are all the angles. So if the angles in the equilateral triangle, or in a triangle in general, add up to 180, equilateral will be that divided by 3, so the angle here is 60. Therefore, the area here is going to be half AB, so half x times x will be x squared, times by the sine of 60. Clearly this here is in degrees because it's 60 degrees. So put your calculator in degrees. You can do a half of sine 60, and that should get you an area here of root 3 over 4x squared. As for the area of the semicircle, well, the full circle would be pi and r squared. Because x here is from C to E from one side of the semicircle to the other, that makes it the diameter. So half of that for the radius will be half x, and that gets squared. But then also, because it's a semicircle, we're going to halve that as well. So what we end up with is a half squared is a quarter, and a quarter times a half is an eighth. So it's an eighth pi, and then x is squared as well. So adding these all together, we should get to root 3 over 4 x squared plus xy plus 1 over 8 pi x squared. This will equal the total area of 50. Now, we're trying to make y the subject. So what we'll probably do is we'll minus everything else over. So you end up with xy equals 50 minus 1 over 8 pi x squared minus the root 3 over 4 x squared. And then if we divide through by x, you just get y on its own, and now that's 50 over x minus an eighth pi, and x squared divided by x is a single x, and minus root 3 over 4, same again, that just becomes a single x. Lastly, we're just going to factorize, so we get y equals the 50 over x, and then we'll take out, so minus x over 8, because that's the fact we can see here. So x over 8, if we took that out, if we took out the minus an eighth x, that just leaves us with pi here. And here, take away the minus is now a plus, take away the x, that's going to go. If you were to divide root 3 over 4 by an eighth, again, that's not divide by 8, divide by 1/8. What that ends up doing is we will lose the 4 on the bottom, but then also we have to times by a further 2. So you end up with 2 root 3. And we now have what we had to show. Now, with this in mind, we want to show that the perimeter of the pool is given by this. Well, for the perimeter, we're now going to need obviously the outside edges. We know that this is x here and this is x here. This will be y and this will be y. And this here, well, the circumference of a full circle would have been pi d, which will just be, pi times x. But here, again, we're going to halve it. So it's going to be a half of pi, and say the d, in this case, it's going to have a value of x here. Therefore, putting this all together, we end up with an initial expression for the perimeter. So p equals 2x plus 2y plus a half of pi x. However, if we compare to this final expression we're trying to show, there's no y in here. So what we're going to have to do is replace the y here with this whole thing. So we have 2x plus 2 lots of 50 over x minus x over 8 pi plus 2 root 3, and then that is plus half of pi x. Expanding the brackets here, we end up with p equaling 2x plus 100 over your x, and then we'll have minus. So the 2 times the x over 8 is going to give us x over 4, but then actually at this stage you're going to times out the brackets again. So what we'll end up with here is pi x over 4, and then your 2 root 3 x over 4. Remember, this is all being minus, so we'll take that away as well. So 2 root 3x over 4, and then plus, actually because we're in fractions, I'll make this a single fraction as well, so the pi x over 2. Now, we have the 100 over x that we're looking for here. We've already found this, so we'll lock that in place. We don't want to change that anymore. However, the rest of this needs to be combined together. And we know we're going to have to take out a factor of x over 4. So let's first of all actually just try to make all of these as fractions over 4. For the 2x, to make that over 4 here, we're going to want to make it an 8x on the top, because 8x over 4 would cancel to make 2x again. And similarly here, if at the end with the pi x over 2, to make that over 4, we'll times the top by 2 as well, because 2 over 4 would cancel to just being over 2. Now that we have this, we can say, okay, you've got your 2 pi x over 4 minus pi x over 4. that's just going to cancel to leave her with one lot of pi x over 4. Now we just have 3 terms, one of which has an 8, one of which will now be a single pi x, and one of, well, just the pi, and then one of here will be the 2 root 3. That is the contents of the bracket, so it would appear we're almost there. So just to rewrite it one last time, you have 100 over x, and then plus, if we take out the factor of x over 4, and we'll do it in the order that we have here. Because this was left here just with these two terms with a pi x over 4, take out the x near the 4, that just leaves you with the pi. From this middle term here, so it's again positive 8x over 4, take out the x over 4, that just leaves you with the positive 8. And then here, so we've got a minus 2 root 3x over 4, so take out the x over 4, you're left with minus 2 root 3, close the bracket, we had what we wanted to show. So, in the first step, we used a value given in the description to create one expression in terms of one of the unknowns. Then in part B, we created another expression for another thing about this shape. And using our piece from the first part of the question, we were able to substitute in and eliminate one of the unknowns to get us an expression all in terms of the same letter. A number of modelling questions may follow this exact same structure. So just okay, we're going to look at what do we have a number of, what expression can we get that equals that, and then when we come up with our next expression, how can we insert the first into the second. Now that we have this, because it's all in terms of one letter, we can now do part C, which is use calculus to find the minimum value of p, giving your answer to 3 significant figures. So calculus just being the umbrella term for like differentiation, integration. So we're going to differentiate this expression for p and find the minimum. Now this is why we wanted to make it all in terms of one letter, because while you can differentiate with multiple letters, that's getting into implicit differentiation. That's something else within A2 that has its own video. Here though, if first of all we actually just rewrite this p expression slightly, we'll say that p is 100x to the minus 1, because x being a denominator is the same as that power, and then what we can say is that this would instead be the pi plus 8 minus 2 root 3 over 4 lots of x, just to get all the numbers together as a coefficient in front of that x. When then we differentiate, so we get a dp over dx, coefficient times power, you're going to end up with minus 100, and then x to the minus 2, and then this will just be plus that coefficient, because when you have x to a single power, that x just disappears. So again, you have this pi plus 8 minus 2 root 3 over 4. To find the x value at which that's true, therefore, this x to the minus 2, that could be written instead as being over x squared. Now the reason why I've done this is while having it in a power form can help with the differentiating, because we're now going to be rewriting and rearranging to solve for x, it may be more easier for you to visualize it this way. Because we're after the minimum value from maximum and minimum in differentiation, we know that tells us that the differential equals 0. So this whole thing here equals 0. Because of that, we could add that fraction across. So you've now got your pi plus 8 minus 2 root 3 over 4 equals the 100 over x squared. So x squared is going to equal 100 divided by the pi plus 8 minus 2 root 3 over 4. And so to get rid of the square, you would then square root. Because these are all real numbers, you can then just plug that into your calculator. That gets you that x is approximately 7.22. Now, you'll want to keep this as precise as possible in your calculator, so I just suggest for this final step, you just use the answer key, or you can note down all the decimals if you want. Either way, though, we want to pay attention to what the question's asking. We've worked out what x is, but it wants the minimum value of p. So we need to plug this back into the P equation here. So it'll be 100 over 7.22 plus 7.22 over 4 times that whole bracket. If you do that and now put that into three significant figures, you get the minimum value of P being approximately 27.7 meters squared. So for this is the minimum because it's the turning point of the perimeter. We're going to show in a second that it is a minimum rather than a maximum point of inflection, but because we know that it's the turning point because the differential equals 0. And also just something to recognise is that even if you hadn't been able to show these first couple of bits, because they gave you the equations that you were trying to make, you can use those in these later parts anyway. So even if you didn't figure out how to work out P, although hopefully you will do, you could still hopefully recognise, okay, it's a minimum of P, so we'll differentiate and solve, so forth. Finally then, we just have to justify that this is a minimum. The question does specify by further differentiation, but that would probably be your method anyway. So yes, we'll want to get a second derivative of this because the second derivative tells us whether it's a maximum, minimum, or point of inflection. So if we were to differentiate this again, right now that was minus 100 x to the minus 2. So minus 100 times minus 2 is going to be positive 200, and that x drops to minus 3. And then this term here completely disappears because it didn't have an x term anymore. Now, when we plug in this x value here, if the second derivative is greater than 0, then it's indeed going to be a minimum because we're saying that the change in the gradient is positive, that the gradient is becoming more positive. So even though you'll be starting negative, you're becoming a more positive number. If it equals 0, it would in fact be a point of inflection because it's basically staying neutral. It's going up one way. It does level off, but then it goes back the same way. And if it's less than 0, it's a maximum because even though we're starting off going positive, the gradient is becoming more negative. So here, if you just do your 200 and then your 7.22 to the power, or again, try to keep the full decimal if you can, this will get you approximately 0.532 if they would go to three significant figures like we had above. Either way, point is, this is greater than 0, therefore it is indeed a minimum. You have proven it. If we can see the steps that we've done here, so how we've taken the details of the scenario to produce a couple of different equations, inserting them into each other, and then when you have an expression all in terms of the same letter, differentiating to find the minimum value, plugging that x value back in, and then showing that it's a minimum by differentiating again. Let's just see how you'd get along with an example of your own. So, you have here this 3D shape. Made up of a trapezium face of dimensions 9x, 4x, 6x, and 5x. And then this face is applied to a depth of y, making this a trapeziumal prism. So then, yeah, we're given the information here and told the total surface area of the six faces is just S. Now, they give you the dimensions again of the cross-sectional area and confirm that certain degrees are 90 degrees. The volume of the letterbox is 9,600. So first of all, show that y equals 320 over x squared, and then hence show that the surface area for the whole thing would be 60x squared plus 7,680 over x. Once you have that, use calculus to find the minimum, and then justify by further differentiation that it is indeed a minimum. So you may wish to think, how can you work out the volume and surface area of such a 3D shape, and think back to the steps we just did with the previous example. Either way, just pause the video, have a go for yourself, and then press play again when you're ready to compare. So, first of all, like we started last time, if we're trying to create an expression, an equation, we need an equal sign. The thing that we have a value for is the volume, so the 9,600. So let's try to think, how can we get a volume for this thing? Well, the volume for a prism is going to be the cross-sectional area times the depth. So if we start off just with the cross-sectional area, this is a trapezium. So for trapezium, your area is half a plus b times by h, or you could split it into a triangle and rectangle if you want and add them together. It gets you the same thing. In this case, your 6x and your 9x will be your A and your B, and the 4x is going to be the height, because they're the parallel sides, and this is the distance between them. So altogether, we get a half of 9x add 6x times by 4x. Work this out, and you end up with an area of 30x squared here. This area is then what we'll apply to the depth of y to get the volume. So 30x squared times by the y gives the volume of 9,600. So trying to make y the subject, to get it on its own, we simply have to divide by the 30x squared. So 9,600 divided by 30x squared. And you should find when you put 9,600 over 30 in a calculator that it does indeed simplify to 320. So it's just 320, and still that's over the x squared. From here, to hence show that the surface area is S, and is given by that. For the surface area here, we're just going to have to do every single face individually, basically. So if we think about, you can break this into two sides, a front, a back, a top, and a bottom. The sides are going to just be the trapeziums that you had already. So it's going to be two lots of this, therefore together that's going to be 60x squared. Not the y as well, because the y was just for the volume. The face here, the area, is just the x squared. For the front, by which I mean kind of this CBFG rectangle here, the base is y, and the height, CB, we can see from here, is 6x. So together, that would just be 6xy. The back is similar. It's going to be the DAEH. The base again is y, but now the height is 9x, so it's 9xy. The top, once again, we're going to have this length here, this CG, is going to be y, but then the quote-unquote height of the DC, that's the 5x, so together that's 5xy. And then lastly, the bottom, the base, once again you have y for your BF, and then the AB is going to be 4x, so 4xy. Adding these all together, because you would be adding up for the surface area, you would end up with S equaling 60x squared plus 24xy. Now here, once again, we noticed, like with the last question, that we have a y term that's not meant to be in our final answer. So what we'll do is we will substitute in the y from before. So you have your 60x squared plus 24 lots of 320, 24x lots of then over x squared, and then the 60x squared plus, and you find that 24 times the 320 will give the 7,680, and then times x divided by x squared leaves you with just a single x on the bottom. We have shown the expression. To then use calculus to find the minimum, we'll then be saying that S equals 60x squared plus 7,680 x to the minus 1. So ds over dx, that's going to equal 120x minus 7,680x to the minus 2. Because it's the minimum, it equals 0, so you can move something onto the other side of the equal sign. So we could say that 120x equals 7,680 over x squared. So if we were to times up by the x squared here, you'd get x cubed, and then we'll divide by the 120. So 7,680 divided by 120, and then to get the x on its own, you would be cube rooting that. This, because these are both real numbers, you can just put into your calculator. Doing so gets you that x is just going to be 4. But once more, we're not after x, we're after the s, so we have to plug it back into the s expression. So you've got 60 times 4 squared plus 7,680 over 4. That gets you a total surface area, or the minimum value of that, of 2,880 centimetres squared. Finally, to Again, justifying with further differentiation that the value is a minimum, we'll have to differentiate again. So you've got your second derivative here. Your 120x is just going to become 120. And this, the minus 7,680 times by minus 2 is going to become a positive here, 15,360 x to the minus 3 now, because you've minused it by 1 again. Plugging in the x is 4. This gets you a value of 360. This is definitely greater than 0, therefore it is indeed a minimum. You've shown a justification for it being so. And that basically is what we're going to do with modelling. Again, it's just constructing these equations, differentiating them, and then just justifying that what we've got is what we were after.